team, I'll be talking about our 2U Cube satellite mission. Thank you for being here, and we're glad to be able to present. So first, to understand the FlipSat-1 and our team, we have to look into the early history of it. The FlipSat-1's parent organization, the Wolfpack CubeSat development team, was formed in August of 2015. We had very minimal satellite experience, so in order to gain some, we practiced on Raspberry Pi emulators, tethered and high-altitude balloons, and we did a captive carry flight. Since then, we've launched one cube satellite, the YSat-1, which is a 1U biological payload, and then we hope to launch our second satellite, the CAPSat-1, in the future. My team, the FlipSat team, hopes to, after all of this, launch a new satellite, the 2U cube satellite mission to study various radiation detection methods, which is the FlipSat-1. So the mission statement of the FlipSat-1 is as it reads, providing space-related experience to students while researching the volatility of single-event upsets within circuit boards with respect to radiation methods. Single-event upsets are anomalies that occur in systems when highly ionized particles hit the binary code within a system. This can cause either data or software to change, which could potentially cause a total mission failure. The ideal orbit for the FlipSat-1 that we're aiming for is within the Van Allen radiation belt, since these highly ionized particles I just talked about are most frequently found in this area. The more amount of single-event offsets that we see in our experiment, the more amount of data that we collect, and therefore a more conclusive conclusion we can come up with. We will be testing on printed circuit boards, and the three methods of radiation protection that we will be testing are Watchdog Timers, radiation hardening, and error correcting code. So our printed circuit boards we hope to get from Prototron circuits, and within each small printed circuit board, we will have an octet sequence. We will assign test groups to each method of radiation hardening, and each test group will have a variant circuit board count. We will have variant circuit board count as certain types of radiation hardening already have a certain amount of information and data collected on them, so different types of radiation hardening need different types of research done on them. In total, however, we hope to have 30 circuit boards. However, the final volume specifications of the FlipSat-1 for our payload has not been worked out yet, so this could increase or this could decrease. Each of these test groups will not only have different radiation methods of protection, but they also have different extents to which the radiation protection will be applied. So this first type of radiation protection that we will use will be physical protection. The method of physical protection that we have chosen is polyethylene. Polyethylene has a really high hydrogen count, and due to this, it's a really good radiation protectant. Because of this, it's already a commonly accepted method of physical radiation protection in industry. Our printed circuit boards will be fully encapsulated by the polyethylene. However, we will have access to it through hosing it, and then we will also connect it to the chassis of the FlipSat-1. Our physical radiation protection will have thicknesses that range from 1 to 5 or 5 to 10 millimeters. Once again, the volume specifications of our payload has not been fully worked out yet, so once we work that out, we will be able to choose which thickness group that we will use. However, for each of these thicknesses, we will have 2 printed circuit boards assigned to them. This is for redundancy in case one of the printed circuit boards has an anomaly or the data does not come through. This way, if one of them fails, we still have enough data to make conclusive answers. Our second method of radiation protection that we will be using is error correcting code. Through this, we will have detection and correction. The way that the detection on our error correcting code will work is that we will have parity checks. That's a sequence that's either followed or led by a parity bit. When the processor of the FlipSat-1 reads the sequence within the printed circuit boards, it will basically sum up the ones and zeros of that sequence. That number obviously will either be even or odd, and the parity bit will reflect whether or not that's even or odd. Through that, should there be a single event upset that has an odd number of bits that are flipped, we will be able to see whether or not there was an event, as we will be able to see a parity bit that does not match up with the sequence. Or if there's an odd number of bits that are flipped, we'll have an odd corresponding to an even sequence, or an even parity bit that corresponds to an odd sequence. We will also have repetitive octet series that will vary. This way we can have forward error correction. Each of our sequences will know which printed circuit board has which sequence. However, once there's a single event upset, we will compare each sequence, the processor will compare each sequence to a known library of sequences that we put in, and basically auto-correct it to whichever is closest. So our third and final method of radiation protection are watchdog timers. We will be efficiency testing them. We will be efficiency testing all of them, and we will be using two different methods of watchdog timers: electronic and physical watchdog timers. Watchdog timers are a common method of protection against single event upsets. Most famously, they were used in the Mars rover experiments. The way a watchdog timer works, as you can see in the diagram, is that they register a hard reset on the system after they get a kit. So that kit can either be from a system or through a clock, and that basically turns a system into a previous state that it was. So our first method of watchdog timers that we will be testing are electronic watchdog timers. So we will have a program running on the internal central processor of the FlipSat-1. This program would then send all of the resets to the individual printed circuit boards within the FlipSat-1. We will measure not only the electricity usage from these electronic watchdog timers, but also the amount of single event upsets that we are catching. The way that we will be able to tell the amount of single event upsets in all of these methods of radiation protection that we prevent is that we will measure the data before we launch the FlipSat-1, during the flight of the FlipSat-1, and after all these radiation hardening protection or correction or reset systems. This way we compare before, during, and after, and this tells us where the single events happened and where we fixed it. So after we compare the amount of electricity draw that these electronic watchdog timers have with the amount of single event upsets that we prevent, we'll be able to get an average cost worth value of these electronic watchdog timers. Our second method of watchdog timers that we will be testing are physical watchdog timers. These are watchdog timers that are registering and executing kicks physically. We're working with an electronic printed circuit board, so of course the only electronic involvement that we will have with physical watchdog timers will be electronic hard resets. Once again, we're weighing single event upsets against the cost of electricity. However, since these are physical watchdog timers, they have a mass, so therefore a weight, which increases the cost of launching the FlipSat-1. So we will weigh single event upsets against the additional physical cost of physical watchdog timers. So the impact that we hope to have with the FlipSat-1 is numerous. The first of which is increasing cost effectiveness for radiation hardening. There's always going to be either electricity draw or weight draw when you're having radiation hardening. So a greater understanding of this radiation and methods of radiation protection will enable especially small satellite teams to better optimize their budget for radiation protection. Additionally, since we're a small team, a student team, we hope to be a stepping stone for either ourselves or other teams when more advanced research is done in the field of radiation hardening. However, foremost, we hope to have an educational benefit to the members of our team. We're a student team, and we hope to either provide aerospace-related experience to students, or at least lead students into the STEM pipeline. So in 2018 and 2019, we submitted the FlipSat-1 to NASA for the CubeSat launch initiative. Unfortunately, we weren't accepted. The two leading causes for this is that we didn't show enough educational value to the members of our team, and we did not have enough technical specifications. So we're planning on resubmitting the FlipSat-1 in the future, and in order to optimize the chances of getting accepted, we hope to show that we have more educational value to students with clear methods and plans of providing students with information and hands-on experience with satellites. Additionally, to increase the technical feasibility of the FlipSat-1, we'll be hoping to receive more feedback from experts in the field, and then working with engineers to make sure that we work out those last technical aspects, for example, our payload volume. So if you have any questions or feedback, I'm Theodore. I'm the co-investigator and student lead for the FlipSat-1. My email is up on the screen, and if we have time, I'm open to questions.
We have time for one question. Yes?
One of the most critical problems with radiation in space is short circuits due to single event lapse. And to detect that, you need to monitor the current of your electronics. So I think you should include that current monitoring in your system.
All right, thank you. We will do that.
Okay, thank you again.